Okay, I think I'm ready. I feel like I'm not. I'm forgetting something. My microphone's on. Let's see about bringing the notes up for today. What is going on with this thing? We finished 4.7? Right? Okay. There was a problem, I believe, in the homework where they gave you a function. Let me look at it and see if it's see if I can discuss it. I don't want to do the whole problem. Did I assign number 33?
No.
Yes?
Oh, I didn't do it.
Okay, they tell you that f double prime of x equals x to the negative 2, and x is greater than 0, and f of 1 is 0, and f of 2 is 0. Did anyone do this problem? Try to get it? Okay. You should have run into a problem because I didn't really go through anything like this. Is that what you were going to come ask me about? Good, because you should have had a question about this. All right, so look, here's the deal. We have, remember last class, we were looking at like the acceleration function. If you do the antiderivative, right, go backwards, antiderivative, then you would get the velocity function. And then if you go back and do the antiderivative again, then you would get the position function, s of t, right? But you could look at this like this. If this is the second derivative of a function, then this would go backwards antiderivative. This would be the first derivative. And you go back again, you get to the original function, right? Same story here. So what they give you is this, which is this one here. And you're asked to go back and find f. You're asked to find f. So we've got to go from here all the way back, right? And they give you that x must be greater than 0. That's just because there's some issues with absolute values and stuff. We won't even really worry about this too much. But they give you these conditions. Oops, I forgot to write in here. F of 1 was 0. Right? They give you these things that we called initial conditions last class. The problem is both conditions involve f. And what we did last class is we went backwards, and then we had a condition here that allowed us to get the constant, and then we went back again, and we had another condition that allowed us to get the constant. And that's the problem you ran into, right? You went back, you couldn't get the constant.
Yeah.
That's what you should have. Okay, so let's walk through this one. So let's start first by trying to figure out what the first derivative is, which means going backwards from this. So what is the antiderivative of that? So this is x to the power, right? That's n. The formula for going backwards is 1 over n plus 1, x to the n plus 1, right? That's the formula, plus a constant. So this should be 1 over negative 2 plus 1, x to the negative 2 plus 1 plus a constant, if I'm following the formula, right? And what's this? Negative 1? X to the negative 1 plus a constant. Question there? No? Okay, so again, last class I said, now let's go try and find the constant, because all this gives us is a family of functions, right? And they would have given us, in the example that we did last class, they would have given us some information about the derivative, right? But they don't give us any information about the derivative. So I cannot nail C down right now, can I? I can't figure out what it is. That's okay. Let's go back and do the antiderivative again. So if I try and do the antiderivative again to find f, I'm taking the antiderivative of this, right? So this is a negative 1 sitting in front. It'll come for the ride. I'll even put negative 1. And then this right here is n, and it's negative 1. That's the special case, right, where the antiderivative of this is natural log. So natural log of the absolute value of x is what it should be. But because they're telling us x is positive, it is just x. Right? Because the absolute value of x is the same as the absolute value, is the same as x. If x is a positive number, then these are the same values. Okay, that's the antiderivative of this, right? What's the antiderivative of c? Cx. C times x. Right? So like if that was 4, the antiderivative of 4 is 4x. Does that make sense? But then, because we took an antiderivative, we always have to have plus c, don't we? But I can't use c because I just used c already. So I'll use d. So now it appears that I'm really screwed because not only do I not know c, I don't know d. There's two things I don't know, right? But I'm given two pieces of information, right? The first piece of information I'm given is that f of 1 is 0. So using the fact that f of 1 is 0, that implies that when I plug what? 1 into this, right? 1 into this function, it should spit out 0. So let's plug 1 in here. Negative 1 times natural log of 1 plus c times 1 plus d, that has to be 0, yeah? Agreed? What is natural log of 1? 0. Natural log of 1 is 0. So this is all gone. And then I have c times 1 is c, c plus d is 0. And that's all I know. This means c plus d is 0. Does that allow me to figure out what c and d is? No, right? I can't tell you what c and d is if I only have one equation. But I have another condition, don't I? And so now let me use that second condition. Using the fact that f of 2 is 0, that means, and I'm just double checking that that's what was given here. Yep. That means that negative 1 times natural log of 2 plus c times 2 plus d must equal 0. Do y'all see that? And that means, well, what is this right here? That's not like a common thing that we're going to know, right? Like natural log of 1 was 0. That was easy. Natural log of 2 is not something we know. Is this the same? Whoa, what happened there? Brought that negative one. Remember, you were the one who pointed that out, like first day, I think, that we could do something like this. Negative 1 comes up as a power. 2 to the negative 1 is the same as 1/2. So these two are the same expressions. And then over here, plus 2c plus d equals 0. So I have how many equations? 2 equations. I have how many unknowns? 2. I'm trying to solve for 2 variables. I have 2 equations. This is a system of equations. And now you have to solve for c and d. So you could do substitution if you want. Right? How could I do substitution?
You can solve for c.
You want to solve for c up here?
Yeah.
So c is negative d, isn't it? So that means I can come down to this equation, and I can replace c with negative d. Can't I? Okay, so that's what I'll do. So I'm going to replace c with negative d. Natural log of 1/2 plus, or actually, when I replace c with negative d, it'll become negative 2d plus d equals 0. Everyone following what I'm doing? And then now just put these two together. That's negative d, right? Move it to the other side. D is the natural log of 1/2. And then that means that c is negative of that, right? C is negative of that? And since c equals negative d, that means c equals negative natural log of a half. Now, I haven't answered the question yet. The question was, what's f? Right? What's f? So here's the function f. F of x is negative natural log of x, and then what was it? Plus, what was it? Plus cx? It was plus cx. So what's c? Natural log, negative natural log of a half? So I'm going to put negative natural log of a half x. Natural log of a half, that's a number, right? In front of x, so that's cx, and then plus d, right? That's the function. Does that match what they have in the back? See if they simplified or did anything different. The answers to the odd are in the back, right? 4, 7, number 33. Nah. Yes. So how'd they do that? They put this negative up, and that made it a 1/2 to the negative 1. And whenever you raise a fraction to a negative, you flip it. So what they did is they changed that to a plus and that to a 2. And then they did this. They rewrote that 1/2 as 2 to the negative 1, and they popped the negative out. They changed that to a minus, and they made this a 2. It's the same answer. Just get used to that, because that happens a lot in this class, if you're trying to check your answers. Questions? I would have taken it the way I wrote it up there with the halves. I mean, I'm not going to take off that. It's the same expression. All right, let's move on. 5.5, substitution rule. So here's where we start getting into, we're trying to find antiderivatives, and I'm going to be giving you rules and steps and procedures and just lots of examples, and hopefully enough to get you on the right track. But before we can begin, I've repeatedly said, let's find the antiderivative, right? Like, find the antiderivative. I've been writing it down. Find the antiderivative. But we need a better way of doing that. So we have some notation. And the notation is that if someone gives you this, if you're given little f of x, then if I need to tell you to go find the general antiderivative of it, we use this symbol in front of the function. That symbol right there. That symbol is called the integral sign. Right? So this symbol is called the integral sign. The function that you're trying to find the antiderivative of right here is called the integrand. And then you always have to, on the end, attach to this, and it's actually multiplication, this thing called a differential, dx. And what this differential is, all right, for us, what we need to look at it as right now, is kind of this thing that tells you what the variable is in the problem. Like, the variable in this function is x, right? This just restates that, and that becomes valuable later to us. That's the way I want you to look at it right now. All right? It's just symbolic. So when I write something like this on the board, that means go find the antiderivative of that function right there. Okay? If you're able to find it, the answer to this should be the capital F, right? That's what we were referring to it as last time. And plus a constant. So all of this together is what we call the indefinite integral. Indefinite integral, as opposed to definite integral. That'll come later. So this is the indefinite integral. That's the integral sign. That's the integrand. That's the differential. This is the general antiderivative, right? This right here is called the constant of integration. And the whole process of actually finding antiderivatives is called integration. Right? So in Cal 1, we did derivatives, right? And that process was called differentiation. In Cal 2, reverse process is called integration. Now, while I've got it here, I want to point something out. Do you remember this? I was going to give you a quiz on this, but I decided not to. Sorry. I forgot what class I'm in here. Hold on. That look familiar? What I was going to ask you in the quiz, I was going to give that to you on a piece of paper, and I was going to ask you geometrically, what does that represent, and geometrically, what does that represent? So what would this have represented geometrically? The height of each of those little rectangles, and this right here would have been the width of each of the rectangles, right? And this means add them up forever, or sorry, add them up to n, and then this said let n go to forever, right? Do you see a similarity? Because I showed you last class that we can do this, right? If we can find an antiderivative. Do you see the similarity in that and this? F of x is the red part, or sorry, I used the same color. This right here is this. This right here is this. And this whole thing right here is basically this. So you know how this is the capital sigma, capital Greek letter S? S? Does that not look like an S? It's like an elongated, stretched out S. So this symbol right here tells you you're taking a sum of an infinite number of things. What it is the height of the function times the width of the little rectangles. See it? That's the connection that I want you to make between this and this. And if you can make that connection, things will be easier later when we start to get into the applications of what we're going to do. All right? So y'all would have done well on that quiz, huh? All right. You want to do it? We can take it? Next time. We'll do it next time. All right. So substitution. All right? We have, right now, the only way we can find antiderivatives right now is if it's a power of x, right? Or it's something we recognize from calculus, right? Something like Cal 1. If I write this down, everyone here should recognize that and say sine x plus c, right? Because it's antiderivative. The derivative of sine is cosine, so the antiderivative of cosine is sine. So that would be correct? So we can do that if we know this. Or if it was something like, you know, x squared dx, we can do that using the power rule. Right? Other than that, though, we don't really have anything else, right? We have no other method. And so this thing we're about to do is called U substitution. And I'm going to give you a strategy for it. But before we talk about the strategy, I want to show you why it is that we need it. So let's look at this. I should point out now before I forget, because I'm prone to forgetting things. When you're doing your homework, if you're doing a homework problem and they have like a number here and a number here, ignore it completely. But then don't go check the back of the book for the answer because it's not going to make any sense to you. Instead, go look at my video and look at the solution. All right? Clear? All right, so ignore these. That comes later. All right. So what do you think a common mistake would be for someone trying to find the antiderivative of this? What do you think someone who... They do... How about this? Right? So this class would be very easy that way, wouldn't it? Yes? if that were the case. But it's not, because look, if you were to check your answer, take the derivative of this, do you get this? No, because you would have to do the product rule there, right? And the derivative of this is a mess, isn't it? It's, let's see, derivative of that, that's 2x times this, plus derivative of this times that, right? And that is not this. So definitely we couldn't go backwards. So, oh well, we tried, right? We tried. So we scratch our heads and we don't know how to do it. And today we're not going to know how to do this either. We will not be able to handle this, all right? So I'm going to adapt the problem just a little bit. I'm just change one little thing here. Just going to make that squared. Okay? Now that doesn't seem like that. You might look at that and go, well, that's going to make it harder now, right? Because I've added this squared in here. But actually that makes it doable. Let's see why. This is where the substitution or use substitution comes in. I'll just show you on the board here. Here's the way it works as a general strategy. What we're going to do is we're going to look at the integral. Ready? Okay, I see it. All right. Now you're going to try and find two things. All right? Something that we're going to call something. Okay? We're going to try and find something. I don't know what it is. It's something, though. Okay? And we're going to try to find something else, which is the derivative of the something. So I'm trying to find something and its derivative, and it needs to appear in there. Also, the derivative, right? The derivative of this something that I find should appear in the numerator, right? So if you have a fraction, we want that derivative part to be in the top, not in the bottom. All right? We don't want this derivative to be trapped inside of some crazy function. Like we don't want this to be in the denominator. We don't want it to be trapped under a square root. We just want it to be sitting up there in the numerator just looking at us going high. Okay? It's okay if this derivative that we see and what we have here is off by a number. That's okay to have happen. It just can't be on the bottom or trapped. Understand? You'll see better when I start doing an example. Once we've determined what this something is and what its derivative is, and then we see them both up there, we're going to make a substitution. And the substitution we're going to use is u is equal to that something. And then once we have that, we're going to go to town. All right? And I'm going to show you how it works. Got it? That's the method. You'll start to pick it up as we do more examples. So let's do this. Let's do this one right here. So do you see something in its derivative?
Yeah.
What do you see?
X squared.
You see x squared as the something?
And it'll be off at a constant.
Everyone see x squared right there? Yes? And its derivative, you see it?
It's 2x.
It's 2x, right? Hold on. My wife came and brought me my phone. You can just show up. Hi, baby. How are you? Love you. Can't be doing that. Do you need to call me or something? Okay. Wow, she never comes here. All right. So you have the x squared. U is x squared, right? And its derivative, which would be 2x. And you're saying you see that,
Yes.
but you're off a little bit. So the 2x you're seeing is this, right? But all you have is x, not 2x. And it's all right to be off by 2. Understand? So I'll also point out, remember that when you're looking at this, this is x times cosine of x squared times dx, right? That's all implied multiplication between these. So you could always rearrange these. I mean, there would be nothing wrong with me writing it this way. Right? That would be okay for me to write it that way? As long as you understand that that x is not inside the cosine. All right. So what do I do once I identify something and then its derivative, which seems to be off by a constant, which was right here? Well, what I do is I come over here to this little equation I've created, and I take the derivative on both sides with respect to x. And so here's the way we'll write it. du dx is, what's the derivative of that? We said 2x, right? Yeah? Now, with this equation right here, notice that we have a dx here. And notice in our integral, right, in the integral, we have a dx there. What I'm going to do is I'm going to multiply both sides by dx here. And these go away. And so what you're left with is du equals 2x dx. Okay? Any questions with that? So what am I doing? Why am I doing this? Well, what I'm trying to get is I'm trying to get something over here to match with something over here. So do you see this x dx right there? That's multiplication. Matches exactly with this x dx right here. Yeah? And this x squared is right here. Yeah? What I'd like to do is I'd like to rewrite the entire problem without x's. And instead of using x's, I want to use u's instead of x's. And that's what we always did when we used substitution, like back in college algebra. It's always about trying to make a problem that was complicated easier by making this substitution. And that's exactly what we're doing with this. So I have x dx here, x squared, and x squared. So I could replace the x squared with what? U, right? Just u. That x squared becomes u. The x dx, I can replace it with what? Yeah, see the 2 here is a problem, right? So what I'm going to do is just scale both sides. Multiply both sides by a half. So if I multiply both sides by 1/2, then the right side is now exactly, right, x dx. And so I can replace x dx right there with 1/2 du. So at this point, I'm going to rewrite the whole problem. You take this. I'm going to rewrite this as the integral cosine of what? U. And then times x dx. X dx is 1/2 du. 1/2 du. With me? Notice the entire problem is in terms of u. All right, so what I'm going to do next is I'm going to take the 1/2, I'm going to bring it out in front of the integral, and why am I allowed to pull a constant out in front? Why am I allowed to do that? It's a scalar, right? So when we were doing antiderivatives before, didn't we say the constant just came along for the ride? Yes? So that 1/2 is just going to come along for the ride the whole time. So what I'm going to do is just get it out of here and bring it down with me and just go find the antiderivative of this. Now, do you know the antiderivative of cosine u if we're treating u as our variable? That's just sine u, isn't it? So at this point, I can actually just write down 1/2 and then sine u. So we're asking ourselves, what's the antiderivative of 1/2 cosine of u du? The answer is 1/2. The antiderivative of cosine u is sine u. And people always ask me, well, what happens to the du? Yeah, technically, it's just not there. This was just kind of a placeholder. It's almost like a 1, but we write it as du to kind of keep track of the variable. When you go to the antiderivative, it's not here. But people like to make it go somewhere, so I just say that turns into the c, so that you don't forget it. Now, are we done? No, because our answer has u in it. The original problem had x, right? So now I'm going to go back and I'm going to resubstitute back in what u was. U was x squared and then plus c. That should be the answer. How could you check it? Take the derivative. So you want to take the derivative real quick? Okay, take the derivative of this. The 1/2 stays there. What's the derivative of sine of something? Cosine of that something, right? Derivative of sine is cosine. So I'm taking derivative here this way. So derivative sine of something is cosine of something, but then chain rule, take derivative of what's inside. So times derivative of what's inside is 2x, right? And that's it. These 2's cancel, right? The 2 and the 1/2 cancel. I'm left with cosine x squared times x, which is the original problem, right? The original integral was this. You see that? So we're trying to make sure our answer here matched up with that, which it does. Just slide that x out front. Okay? Let's do another one. Let's rule out some other things. Can we use the power rule on this? That thing from last class. Can we use that rule? That only works if we have x to powers, right? Here we don't have x to powers because we have a fraction. There's no way to split this up and get individual powers of x, right? That square root in the bottom is causing major problems. So that won't work. Do we recognize this as something from Cal 1? Like, obviously, that's the derivative of blah. No, right? So the only other thing we have is this substitution thing. So you're looking for something in its derivative. X squared plus 1. The derivative of that is 2x, which is exactly sitting up there. So there's the something. Its derivative is up top, which is good. Are we off by a constant? No, it's exactly dead on, isn't it? That's a great thing. So what I'm going to do is I'm going to make a substitution. U is equal to what? X squared plus 1, right? Then I'm going to write du dx is 2x. I'm going to take dx and multiply on both sides. And then I'm going to play a matching game and see if I can make this work. So to do the matching game, I think what I'll do is I'll rewrite this problem. I'm going to slide the 2x out because it's in the top, right? It's in the numerator, so I can just slide this out like this. This is the same problem. And I'm only doing that because I want to match this. See that? I will be able to replace that entire blue piece, right, with du. And then I will be able to replace x squared plus 1, the whole thing, right, with u. Understand that? So if I were to now go ahead and make the replacement, this would be integral, and then what? 1 over square root of u, and then this would be du. Yeah? Okay, but what do you do with that? What's that? You want to push that root up to the top? It's fine with me. And then make it u to the negative half? And can you handle when you have u to a power by itself? That's just like x to a power, right? So now you're going to use the power rule from last class on that. So what would the power rule give us here? We're going to add 1. So 2u to the 1/2 plus c. So remember, n here for us is what? Negative 1/2. So you're going to add 1 to that. Add 1 to negative 1/2, and you get positive 1/2. 1 over 1/2 in the front would be 2. So I'm assuming that you've got this stuff down now, that you've practiced it enough that you're comfortable. Are we done? No. Nope. You have to always go back, right? Switch back. What was u? So this is going to be equal to 2. U was x squared plus 1 to the 1/2, right? But that's the same as the square root. And then plus c. That's it. Could we check it, or you want to check it? You believe me? Okay. But you could check it, right? All right. Now I have a question, because I know some of you have seen this before, because I know I did talk about this in Cal 1 at the end of the semester. But why not have done this? Like, I have this one here, right? But if I did this, right, and I did du dx, I would get 2x dx, 2x. And then when I brought my dx over, I would have this, right? And that would have still matched. And I could have replaced this. And then this right here would have been this, right? So I could have done that, right? But the thing is, where would I be on the next line? 1 over square root of u plus 1 du. And on that, you can't bring that up and just make it a single power of u. Does everyone understand you couldn't? If you tried to bring that up, it would look like this. Integral, it would be u plus 1, the whole thing to the negative 1/2, right? And you cannot put the negative 1/2 on each one of these. That's a big no-no, right? So you wouldn't be able to do a power rule on this. You'd be stuck still. Understand? So what you want to do when you pick this u is you want to be real careful about it. You want to pick enough that you actually have something in a derivative there, but you don't want to pick too little, you don't want to pick too much. So if by me grabbing the 1 at the same time, it had no effect on this, right? But it helped me at this stage, yes? Now what if I would have been super ambitious and I would have been like, all right, I'm going to take the whole denominator. I'm going to take u is equal to the whole damn root. I'm just going to take it all. Now you're taking too much. Because what's the derivative of this? 1 over 2 root x squared plus 1 times 2x, which is x over root x squared plus 1 dx. Sorry. You see that? You with me on that? So if you rewrite this, bring the dx to the other side, and you try and play this matching game, you're already going to use this whole thing as u, aren't you? Right? So this is off the table now. This has to somehow match up with these two. It doesn't match, does it? You got all this root crap in here, and you don't have any more roots to play with. You already got that one. That one's already eaten up by the u, isn't it? So do you see how you took too much with this? X squared's not enough. Square root of x squared plus 1's too much. X squared plus 1, perfect. But that sometimes takes a little bit of time and practice to get good at picking the right thing. Questions? All right, next one I'm going to put up. You're going to play with it, see if you can get it. All right, play with that. Sure.
You're saying including the radical is too much. Ignoring the constant of the one is too little. Are there situations where including the radical is good, or is that more complex problems we don't need to worry about?
If your integrand would have been more complex and would have had other stuff in it, then it would have possibly been fair play. So is there a problem that sometimes you will include the radical in a substitution? Yes, just not that one.
And is it just practice and time to get used to it, or is there a golden rule? It's like if it's in the numerator, include it or don't?
No. Yeah, no. So yeah, it's a good question. As you're going to see as we proceed through these things, there's not going to be some like one cookie cutter way of doing everything, or this type of problem, always do it this way. And that's what makes the class harder, is because there is nothing. Like in Cal 1, you have chain rule, and there's no variation of it. It's just the chain rule's the chain rule. Product rule is product rule. This way, there's nothing. So it's pattern recognition, practice, practice, practice. Things become second nature. You start to see it, and yeah, so. When you get your U, raise your hand, and I'm going to come by and see if your U is good or not, okay? Okay? Yep. Let me see.
It's my U. Because it has to be part of the denominator. It has to be also part of the numerator. The derivative has to be part of the numerator, which the numerator is 1, right? Or am I-
Well, let me address what you're doing.
Right.
I'll go talk to everyone about it. Anyone else have their U yet? Yes? I heard yes. I didn't. Who said yes? Yeah. Okay, so what was Alex? Okay, so Alex is suggesting possibly doing U as X. And yes, you can do that. However, watch what happens if you ever do this as your substitution using this technique. Watch what happens. Du dx equals 1, right? Which means du equals dx if I bring the dx to the other side. So what's going to happen is every x I see, I replace it with u, and dx I replace it with du. And the whole problem would become square root 1 plus 1 over x is u, the bottom is x squared, u squared, and dx is du. And all you've done is rewritten the problem in terms of u. So yes, you can do it, but it gets you nowhere because you're just changing the variable from x to u. That's all. So in this method, that would not be a substitution you want to make. It's got to be something more than that. Well, I don't know. That's what I'm having you try and figure out. So I know I've got at least 2.
Maybe.
Talk to each other. Help each other out. Okay? Have you tried it?
No, I'm just, we said to call you if you have
Okay.
you.
Try it out. Same thing? Yeah, try it out. See what happens. So are we jammed up here? Okay. Talk through it. I'll give you some more time.
Problem, you use the denominator value, and without sounding like a lazy ass, I figured that would be a good one to just use as you use substitute, because you can turn u is equal to x squared into 1 over x if you need to. You can take the derivative of it, it's 2x. I just thought it would be a clean and easy.
So if you're suggesting maybe letting u be x squared,
Yeah.
then the derivative of that is 2x, and do you have that somewhere? Do you see 2x anywhere? So I don't see a 2x anywhere, unless you want to mess with that, but that's trapped in a bunch of complicated shit, and you don't want that. You want that derivative, wherever it is, to be free from stuff. Okay? You're thinking one, what do you have? Okay, try it. Work it and see what happens. You got one?
Is it enough or no?
That's not enough. That will work, but if you go a little bit more, you'll get it. So grab the one with it. That's good.
So it's just getting this whole thing right.
Try it now. Work through it and see what happens. That's correct. That'll work.
Okay, so I think we're stuck on the same. We're the same u. We get to the same du.
Look, you did antiderivative or something. You're doing derivative right now.
I'm doing
1 plus x to the negative 1.
Same thing. You need to take derivative.
Because then when you take the derivative,
The derivative of this, not antiderivative.
which is the
Are
same
you,
as
how are you doing over here, sir? Yeah, there you go. Okay, same thing. You're going from here to here is derivative. So work that again. You did antiderivative also. Look, when you pick your u, right, whatever that is, this next one is the derivative of it. Okay, not the antiderivative. Did it finish out? Okay, so you're still. The whole thing? No. Oh.
It's on top, up top.
But with the radical? Oh, the whole radicand? You can if you want. Try it. Did you? Well, you did? What happened?
I didn't think I got it.
No, you got it.
Really?
Yes, I'm going to help you. That's the same problem. Is that not the same problem? See, this x squared on the bottom, if you pop it out, is really a 1 over x squared. And if you remember from Cal 1, what the derivative of this is. That's the antiderivative. So I'm going to give everyone the correct substitution right now, but I want you to work through it yourself. Let's see what you get. I'm going to rewrite it this way. This is this. Now work through it. Did you get somewhere with it? Okay. So you just pop that up. That's another way to do it. That's fine. And then the negative to the other side. Negative came out. U to the 1/2. Added 3 halves, 2/3. Yep. Looks perfect. Now,
plus c, right?
yeah, plus C. So if we check it real quick, you bring that out, right? They go away. You get a -1. All of this to the 1/2, which is that. And then you take derivative of the inside, and you're going to get -1 x to -2. The negative that was out here cancels. Yes, that's right. Plus C. Good. So how did you see this? Like, how did you
Oh,
see
I
that?
immediately rewrote that as
X to -1.
next to the -1, and then
you just-
derivative you subtract 1, and
Yeah.
so it was only going to be off from by negative.
Okay, so you just saw all that?
Yeah.
See, I can't teach that.
Yeah,
That you just either see that or you don't,
Yes.
right?
I guess
Okay.
so.
And I think that is directly correlated to how comfortable you are with seeing. You saw the derivative. You saw the derivative of x to the -1 was going to be something with x to the -2, right? So that's why I said in the beginning, the stronger you are with your Cal 1, the easier it's going to be going backwards. Anyone have questions? Still working it?
So you
Okay, so how'd you get -x?
because it's in the derivative of 1 over x negative x.
How are you getting that? 1 over x is x to the negative 1, right? So when you take derivative of this comes out, and then you subtract 1. So negative 1 take away 1 is negative 2. And that's the same as negative 1 over x squared, which is nice because that's what we have out there.
Use off by a constant.
You're off by constant. Yeah. Who said that? Oh, I'll be right back. Yep. Yeah, it is, but yeah, replace u. Yeah, plus c. Yeah. That looks right. Good. Good.
I took the negative out.
Yeah, negative out. Root u. This is u to the 1/2. See, you're taking the derivative again. Now you do antiderivative. Yes. Okay.
This is what I have so far.
Yep.
So it's right?
That's right.
I'm
Yep.
going to do dx cancel and then get the du out of it.
That's right. Remember, what you're trying to do is see this over here somewhere.
Yeah.
And do you see it up on the board how I peeled that off?
Yeah.
Okay, when you have this right here, just remember that that really means this. Right?
Yeah.
You see it? Okay.
All of my, okay, u's there, du dx is this,
Yep.
du is this, right?
Uh,
Because if you did that over 1, or do you not combine them? Do you just leave it as?
Oh, that's dx. You can leave it like that, or you can do this. I mean, I would leave it like this.
Isn't it du? Because I thought we times dx by both sides.
Yes.
Du.
Uh-huh.
So yeah, it's a negative dx over there.
This is, but you put the dx on top. You can do that. You can, but just realize, like, if you're going to peel things apart in the original problem, the dx usually sits out here by itself. You don't have to.
That's fine.
Okay, so look, you see this 1 over x squared dx?
Yes.
If you wrote your side like this, you could kind of see the 1 over x squared dx a little easier.
Right.
The only problem is you're off by negative.
Oh, I'm not done there actually. There. But what as you came over as I was writing, but my big question is now when I go to try and do u substitution, I have a value for u that is this, but I don't see how I can plug in for the square, because if I just say u squared, that's, do you know what I mean? I don't know how.
You're going to replace 1 plus 1 over x.
With u,
with
which
u.
is what I did, and then I erased it because I had no idea what to do with the x squared.
Let's go back to this. Erase that negative sign, okay? Because that's not in the original problem. Okay? So this is just peeling it apart, right? Okay. This right here is going to become square root of u. We agree?
Yes.
Okay, so the new integral,
what I
square root
wrote.
of u. Put the integral sign out front. Okay. 1 over x squared dx. Right here, I want you to rewrite this as negative 1 over x squared dx, and on this side put equals du. So you need to replace this. 1 over x squared dx, you have it, 1 over x squared dx. It's just, this is negative, that's positive, right?
And you just had me erase the
Multiply,
negative.
hold on, no, because you can't mess this up.
Okay.
You got to multiply both sides of this by negative 1.
1.
So multiply that by negative 1 becomes plus.
Plus.
That over here becomes negative.
Negative.
So you see this entire expression is this side. So this entire expression is du. So just write du next to that. Negative du, yes. Bring the negative out front in front of the entire integral.
And now, why is it that we can do that with this? I understand if we're doing it with some coefficient, but are we just going to call that a coefficient?
I'm not sure I understand.
When we did that before, it wasn't a variable, it was like 4 or something. It was just some number, some constant.
No, I didn't tell you pull out du, though. I told you pull out the negative.
Ah.
Just the negative, like a negative 1.
Yeah.
Leave the
that
du
I
in
get.
there, yes.
That's fine.
Leave the du in there. And now, this is just power rule. This is u to the 1/2.
Yes.
So you're going to do u to the 1/2 du. So use what we did last class, right? This is your n.
Sure.
You're going to do 1 over n plus 1 and all that stuff, right? But it's going to be u instead of x. Okay? Do that part now and then see what you get. That's right. That's good.
So once it's du and then it becomes
Yep.
negative x squared, how do you make this negative?
What you're going to do instead, you're not going to try and make this negative. You're just going to switch this to a positive by multiplying both sides by negative 1.
Okay, so that would equal negative?
Negative, so write negative du we'll just rewrite the whole thing. Negative du equals 1 over x squared dx. Now, you're going to rewrite this entire integral. So put integral sign here. You're going to have square root, now hold on. Yeah, okay, good. U, right? And then times, now, negative du. And that's really like negative 1, right? So go ahead and pull the negative 1 out of the integral. And then square root of u.
The negative 1 that we brought out, we run it back through at the end.
At the end, you'll run it through. And now just follow that. Yep, got it? Okay. I think we're, you feel like you made progress there?
Yeah.
Okay? Somewhat? Do you want me to run through it, or you want me to run through it?
Yeah, please.
Okay, this is the correct substitution, which could be rewritten this way. The reason why is because I can see already. Why? Because I've done enough derivatives in my life to know that the derivative of 1 over x is going to have something to do with 1 over x squared. Right? The derivative of this is going to have an 1 over x squared in it. If I don't know that, this is going to be a lot harder for me to do. And I'm almost going to have to just take a shot in the dark at it and hope that it hits. So, assuming that we took this, here's what it is. I'm going to take derivative on both sides. Derivative of 1 is 0. Derivative of this is negative x to the negative 2. Right? And then I'm going to go ahead and, I'll leave that there. I'm going to go ahead and put the dx on the other side. So I move the dx to the other side, and I rewrote this as negative 1 over x squared. Now, the original problem here, I had split it apart just to help you see the pieces. Numerator, this split out was 1 over x squared dx. And I almost have 1 over x squared dx. It almost matches. We're just off by a sign. So I multiply both sides of this equation by negative 1. If I multiply left side, I get negative du. The right side, this becomes plus. And now, hopefully you see these match exactly, don't they? This matches exactly with this. And this is what's under the root. So I can replace this piece with u. I can replace this entire piece with what? Negative du. Yeah? So we've got new integral square root of u times this whole piece, which is negative du. I go ahead and I pull the negative out of the integral. I rewrite square root of u as u to the half. And then I just use the power rule from last class. So the negative stays out front, right? Negative 1, I'll say. And then I do my little adding 1. And so when I add 1 to that, I get 3 halves. And then in front of it, I do 1 over 3 halves, which is 2/3. U to the 3 halves plus some constant. Now replace u. And I'll also put these two together. So negative 2/3 u, which was 1 plus 1 over x, to the 3 halves plus c. That's it. What lesson can you take away from this example? Don't overthink? Is that what you're saying? Okay. I hope you all have lessons that you're learning from this. The one that I would say is the most valuable is you're going to have to do a lot of these to get comfortable. Okay? You're going to have to do a lot to get to a point where you're very comfortable with this concept. You can't just do like 2 and be like, yeah, I should be able to handle that from here on out, you know? Because they can come and they can be ugly. Do what? Can I do a check? Okay, so if I do a check, the derivative of this would come out, right? And when this comes out and hits this, I just get a negative 1, right? So I get negative 1. And then all of this raised to, I subtract 1 from this. So 3 halves take away 1, I get 1 half. Times, then I need the chain rule, the derivative of what's in here. Derivative of 1 is 0. Derivative of 1 over x, we already did that. That's negative 1 over x squared. Right? This negative and negative become positive, so I don't even need this anymore. And then if I just take this and I slide it underneath this and change that to a square root, I have the original problem. So it works. So remember, this is where my videos for the homework start. Right? So you remember all the homework problems that I assigned for you? I have a video of me doing each problem. So I recommend what you do is you sit there and you try and do these problems on your own. You make a substitution, see if things work out. If you get hung up, you go bring up my video. You see what my substitution was. You pause the video, you try my substitution, then you watch the rest of it and see if we get the same thing. Watching my video and just seeing me come up with the substitutions doesn't help you. You've got to be the one that sees the substitution. But at least you're not hung out to dry, right? With nothing. Let's try something else. Did you say that was easy? Or that's easy? You see something in its derivative? What is it? 1 over x is what? Is the derivative of natural log of x. So the something that you see is the natural log, and its derivative is 1 over x. So maybe it might be more efficient to maybe split this up like that, just so you can see it. Like, look. Natural log of x. Not 1 over natural log of x, but just natural log of x. Its derivative is right there, isn't it? Okay, so that's a good candidate for our u. U would be natural log x. The derivative, now every time I've done this derivative, right? Every time I've done it, I've done du dx, and I've always taken the dx to the other side. So I'm going to stop doing du dx, and I'm always just going to write it with the dx on, with the dx on the other side. Is that okay with you if I start cutting that middle step out? All right, so now the matching game. Can we match this up exactly with something over there? Yes, it's actually this and this together, isn't it? So I can handle that part. And then the natural log of x is just this little denominator right there, right? So I should be able to rewrite the whole problem, right? It should become the integral. What's the red part going to become? Du. So I'm going to slap that on the end. And then what's the blue going to become? U, but it's underneath a 1, right? So 1 over u? What is the antiderivative of 1 over u? Natural log of u, right? Actually, we should do natural log of the absolute value of u, just to make sure that we don't have any negatives inside the log. And that's it, right? Except we need to switch back, like get x back in there. So what was u? Natural log of x plus c. So the antiderivative is the natural log of x. And how could you check it? Take the derivative, and it would work. Chain rule. Start with the outside function. Derivative of natural log of this is 1 over it times the derivative of what's in here, 1 over x. And that's exactly what this is. Okay, let's try something else. Pardon me? I just didn't hear you.
Oh, is the U just the whole bottom one?
Do you want it to be? You're in control. Whatever you want.
Yes.
You want the whole bottom to be your U? Why do you want that?
Because when you take the derivative, it'll give you the numerator.
Yeah, the derivative of the bottom is the derivative of the denominator is the numerator. Right? Man, that worked out beautifully, didn't it? So when I put my dx over here, remember I said I'm going to stop multiplying both sides. Just be careful on this, because this is the first time we've had two terms over here. This dx is being multiplied times both. So just be aware of that. But that's okay, because if I were to rewrite this problem and split it up, then if I slid the 2x plus 3 out, I would have to do it like that. Right? Both of them would have to come out together in parentheses. And so, again, this is like a perfect match, isn't it? Awesome. Awesome. That's this. And then this piece right here is that piece right here. So how is that integral going to transform? That's the final answer, right? This is really 1 over u, and then this piece right here is du. And that's just natural log of the absolute value of u plus a constant, and then replace u. Anybody have a question on this one? Later on in this class, you're going to see this happen, and we're going to get it to this point. We're going to be like, yes. All right, we're going to be like, yes, we got it to something we can handle here. Okay, I want to give you a problem. See how we do with this one. It's not any harder or anything, just so what are you thinking here? You want to make a u substitution, use x squared plus 1? Because the derivative of that would be what? 2x dx. And you don't have exactly 2x dx, right? You're off by 2, aren't you? That's okay to be off by 2? So I could have rewritten this as 1 over x squared plus 1 times x dx. I need this to match with this over here, right? Divide both sides here by 2. And we should get them to match. Any questions?
Regular question.
Yeah.
What's the dx actually in the problem? You said that's something later that
It's
we'll
called the differential, okay? The two ways I can answer that question. Back in the geometric representation, it was the width of the rectangle. It has to be there, right?
have? Oh, okay.
Okay, in terms of this, it's a 1, okay? Because the derivative of x is what? 1, right? If x is your variable, right? So if I sit here and I say, hey, look, everyone, take the derivative with respect to x of x, then everyone says, oh, well, that's 1, right? But if I say, what's the derivative with respect to x of u, then the answer is not 1, right? This is du dx. So when we make substitutions here, right, du, when I take derivative left side, it is not just 1, right? It's this crap over here. So when we have this dx, it's 1, it's always been 1, but we're not writing as 1 anymore, we're writing as dx, and that's useful because when we do the substitution, it'll be replaced by du. I don't know if that makes sense. It's 1 initially, but we need it to make substitutions. Yeah. Imagine, I guess you could, I don't know, I'm not going to go down that road. Okay, are we comfortable continuing with this? What is this going to be? 1 over u times 1/2 du. And so I can pull the 1/2 out. And so the answer would be 1/2 natural log u plus c. And u is x squared plus 1. So this should be 1/2 natural log of the absolute value of x squared plus 1 plus c. Do I really need the absolute value around this? No, because that's always positive, isn't it? So I don't necessarily have to have it. Now, the reason why I showed you this example is because if I change this problem to 1 instead of x, your answer would be what? It would be arctangent. That would be something you should recognize as being the derivative of arctangent. So the antiderivative of this would be arctangent x, and you'd be done. But a simple change like that means it's no longer arctangent. It's going to be a u substitution. Understand the difference? Okay. Those are those little subtleties. All right, so far all the substitutions that we've had have been pretty natural. In other words, we've seen something in its derivative, right? That's the method I told you to use. Hold on, trying to remember. Oh, yeah. Okay, so let's discuss this. If we had x's to powers, right, we could use a power rule as long as they're separated by addition and subtraction, right? If I had a bunch of x, like x squared minus 3, blah, 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 bunch of x's, I could just do each one separately. And that is not the case here, right? I don't have a bunch of x's separated. But I could, if I took x plus 4 to the 302nd power, if I could take it and multiply it times itself, 302 times, boil it all out, then I would have a bunch of x's, right, separated by addition and subtraction. And then after I figure out what that big long string of things is, I could just pass an x through it, and it would just bring the powers all up by 1, right? And then I could do each one separately. So do we want to do that? Absolutely not, right? Nobody wants to expand that. Now, maybe if it was 3, I'd want to. But 302, no way. So we can't do that, right? You want to start that? You'll probably be done by the end of the semester. So we don't want to do that. The only other thing is the substitution, right? But to do a substitution, we need to see something in its derivative, right? That's what I've told you. Do you see something in its derivative?
X and x plus 4.
X, how do you mean?
Well, I guess if you have like half of x is x plus 4, just kidding.
Don't be kidding around with me like that, please. U is what? I think everyone's in there looking, and you can't really see something in its derivative, right? And we already said don't let u be x, right, Alex? Because if you let u be x, all we do is rewrite the problem, right? And I agree with you. There's not something in its derivative there. So I'm kind of the bearer of bad news at this point, which means that substitution is sometimes a technique that you use and you don't actually see something in its derivative. In other words, sometimes you use substitution when it doesn't look like you need to. Which means that when you look at an integral and you're stuck, you have to try something. You have to be willing to take a swing at it. So I'm going to take a swing at it right now. And I'm going to try this. And it doesn't seem at all like that's going to get me anywhere. Because the derivative of this is what? 1 on the right side, right? Now, do I have a 1 in here? Anywhere, right? There's always a 1 somewhere, right? So the derivative of that is there, right? But it's kind of like, come on, seriously, is this going to get us anywhere? So let's try it. The derivative, this is du. The right side, what's the derivative of x? You told me 1, right? Derivative of 4 is 0. So I'm just going to have dx on this side, right? Right? Okay. Now, let's see. Can we play the game of matching? Dx, I'm going to be able to replace that with du. X plus 4, I'm going to be able to replace that with u. But what about the x out there? I can't leave the x there. My integral can't have u's and x's mixed together. Do what? Can I take the x out? No. Now you can take constants out. All right? Now, I'm glad you mentioned that, because it's just like when you take a derivative. If I was asking you to take derivative of x sine x, right? Take the derivative, Cal 1. You can't say, you know what, I'm just going to ignore sine x and just do derivatives of sine x. Same thing with this. You can't just ignore the x and do the antiderivative of what's left. So, all right, so I can replace the stuff in red I'm good with, right? This x, I'm not. However, y'all see it?
You can solve for x.
This is an equation, right? I drew that, I wrote that equation right there. Right? That's the relationship between u and x. U is equal to x plus 4. That means x is equal to what? U minus 4. Right? Good. So I will be able to replace this piece right there, right? Now let's see if that helps. Let's see if that saves us or not. This integral is going to become x, which we just said is u minus 4. I'm going to have to put that in parentheses, right? And then what's x plus 4? U raised to what power? 302. And then dx is du. Did that help us or hurt us? What, I mean, did that help at all? What was the problem when we were doing this? We said the only way we could do this is if we expanded this 302 times, right? Look at this. You don't have to expand anything. It's u, isn't it? And then you have parentheses. Can you distribute that u through this parentheses? Yes. What's u to the 302nd power times u? U to the 303rd power. Isn't it? So this becomes u to the 303rd power. Now distribute it to the negative 4. Negative 4 u to the 302, and then du back here. Do y'all see that? Y'all see that? That substitution, which doesn't look like it's going to get you anywhere, actually allows you to rewrite this in a way that you don't have to expand something. And this, you can just do each one separately, can't you? Power rule on each of those? Questions? So I'm going to continue here. Antiderivative now. The antiderivative of this, 1 over 304 u to the 304, right? Minus, the 4 is going to come along for the ride, 1 over 303 u to the 303 plus c. But what was u? X plus 4. So this is 1 over 304, x plus 4 to the 304 minus 4 over 303, x plus 4 to the 303 plus c. If you take the derivative of that, you should get back this. I'm not going to check it. But it would work. I feel good that it would work. You don't believe me? How are you doing here? Is this okay? If that was just cosine x dx, the answer would be sine x plus c, and you'd be done. But it's not going to be that because of the 4, right? What is your, well, I should say, does your gut kind of tell you that this should be there, though? Right? Because what's the derivative of this? Cosine of 4x. But then chain rule, you would have to take derivative of what's inside, which would give you what? A 4, and you don't have a 4 over here. So what should I do over here to account for it? Put a 1/4 out here. Now would that work? Yes? That's it. I just want you to see that, yes? Believe it or not, though, this is a u substitution. Okay, it's u is 4x, du is 4dx. So this is going to be replaced with u. And then to get dx, I have to get this piece, right? So what would you do on both sides here? Divide by 4, 1/4 du equals dx. And then when you rewrote this problem, you would actually have integral cosine u times 1/4 du. And then you go, do you see this? Okay, but you don't need to do that. What I want you to see is that anytime you see this, you just have to scale it down. Let me show you another example. That's pi. What's the antiderivative cosine pi x? Sorry. Equals what? 1 over pi sine pi x plus c. Understand how this is working? You do not want to be doing substitutions on problems like this. It'll take you way too long, all right? How about this one? What's that? You know the antiderivative of sine is negative cosine, right? But you have to account for the 4. So negative 1/4, good. Negative 1/4 cosine 4x plus c. We're almost getting a general formula here, almost. I want to give you a few more examples. What's wrong?
I don't understand. I'm not understanding why you're getting the 1/4 and all that 1 in front of it.
Okay, take the derivative. What's the derivative of cosine 4x? Negative sine 4x. Now derivative of what's inside 4,
Okay,
right?
there it is. Okay.
So you want it to turn out to be that. So you don't want the negative there, okay? And you don't want the 4 there.
There you guys.
Got it?
Thanks.
Let's do another one. Antiderivative of secant squared of negative 3x dx. So what's the antiderivative of secant squared? Tangent. So this should be tangent of negative 3x, right? But you have to scale it because you don't want that 3 to pop out. And negative 3 would pop out. You don't want that. So what are you going to have to put in front of this? Negative 1/3 plus c. Give you another. What time do we end? 12:40?
Yes.
Okay, so how about this? Let's go back to cosine. That's an easy one to work with. 5x plus 1. Ooh, does that change things?
No.
Doesn't? So what will I have here? Sine, right? 5x plus 1 plus c, and then 1/5 out there. So the plus 1 doesn't matter. Why doesn't it matter?
Because it used to be 0.
Because when I take the derivative of the inside, the 1 doesn't really make a difference, does it? Derivative of that's still going to be 0. I'm going to get the 5 to pop out, and I still need to kill the 5, don't I? So what we're kind of getting here is almost like this general idea that if you are, in general, if you're trying to find the antiderivative of a function, and inside of it you have a linear expression, right? 4x, pi x, negative 3x, 5x plus 1. Those are all linear expressions in x, aren't they? Then the antiderivative of this is just the antiderivative of that function, right? With the linear expression plugged in. So whatever the little function is, find its antiderivative, plug in the linear expression, but then you have to scale it, don't you? 1 over a is what you're going to have to scale it by. That's kind of the general idea. I want to give you maybe 2 more to make sure you understand this. How about let's see if you're really picking this up. Do you see a linear function or a linear expression sitting inside of a function here? Yes? Linear expression sitting inside of a function. What is the function that it's sitting inside of? No, that's the linear part. That's just like something to the 7th, right? Do you know the antiderivative of something raised to the 7th? What is it? 1/8? That's something to the 8th, right? That's the antiderivative? But plug the linear expression in, right? But put 1 over a out front, which will be 1 over 80. But I have to put that 10, right, out here. Do you see that? 1 over a. This is the antiderivative of the function. We're almost looking at it as being like u to the 7th. The antiderivative of u to the 7th is 1/8 u to the 8th. But we have to account for that 10 out front, so we scale it by 10. Now, this is something that's not absolutely necessary. You could have done this with u substitution. This is a timing thing. This is a matter of how long is it going to take you to do problems if these things, if something like that takes you 10 minutes. That's going to hurt you on a test when that's just part of a bigger problem. I said I'd give you 2 more. Let's see. Now, we haven't talked about that yet. What is the antiderivative of e raised to something? Itself, right? So this should just be e raised to itself. To that something. And that was linear, right? So what am I going to need to do? I need to do 1 over what out front? -3 plus c. And if you don't believe it, just take the derivative yourself, right? Take derivative of that, and you get what? Itself times derivative of what's up here? -3. You don't have that out there. Oh, wait, I put that in. Now I have it, right? It kills it off. So the sooner you pick that up, the better off you'll be. Any questions? All right, so I think that's probably enough. We won't, I hate ending class early because at the end of the semester I always wish I had an extra 10 minutes. But let me just state something here. Starting today with today's homework, all right, you must be proficient with this by the next time I see you, all right? Now, you don't have to be a master of it, but you can't be getting hung up on little basic substitutions where it's very obvious, very clear what the substitution is. So from here on out, this is a marathon, all right? This is, can you finish and master the material from today's class before I see you again? Because from here on, it will be relentless. It will not stop. The methods will keep coming and keep coming and keep coming. So tomorrow's class, Tuesday's class, we go to the next technique, which is called integration by parts. We'll spend a day, if not 2, on that, and you will need to have mastered that by the time we move to the next technique. And then the next. So there's no such thing in this class as, you know what, I'm just going to study like 2 nights before the exam type thing. It will not happen that way. All right? So work hard. You will get rewarded for hard work in this class. And even sometimes when you work your ass off, it's still not enough because this stuff just gets hard. All right? So good luck. The what? Oh, roll. Yeah, I keep on forgetting that. Oh, you want your quizzes back, right? The problems? Do I not have them up here? Okay, well, I did.
The homework.
Yeah, it's 5.5. Hold on, I'll put it up here.
Is it on your schedule?
No, I don't put the homework on the schedule. I can tell you it's right here. It's open. While I'm doing that, here's the sign-in sheet. Just pass that around. This is page 306. Now, I told you I've done the videos for the solutions to all these, but I don't remember which ones I've done. So,
Did all of them.
did I do all of them?
Yeah, I watched the last
1 through what? Do you know? I probably did 1 through 52.
You did 1 through 36.
1 through 36?
Not mistaken.
Okay. Well, that would be the minimum, 1 through 36. But yeah, there's no harm in trying 37 through 52. The only thing I'll say about 37 through 52 is that those are all integrals that have numbers here and numbers here, so the back of the book won't make sense to you when you look at their answers. I'll have to check. Are you sure I only went up to 36, or that's all you remember? Okay. If you want to, 37 through 52, if you get bored and you have enough time, all right? But this is the bare minimum of what you need to do. I would start with doing all the odds maybe first, because the answers are in the back of the book, but you've got the videos, so you can always reference that. Yes? You do them, but don't, just ignore the numbers, and then when you look in the back of the book for the answer, it's not going to help you. Yeah.